So that binding energy per nucleon, let me look at you. That binding energy per nucleon graph, it kind of, it depicted the probability of a fission occurring. I knew that I had to have something greater than iron 56, and that didn't really mean I could do it. I really needed to get a very weakened, essentially, isotope, something that had a very high mass number. That's why we use heavy isotopes like uranium and thorium and plutonium, because the binding energy per nucleon is going down as the mass number goes up. Very key. Now, the way we're going to liberate that energy is we're going to essentially make the isotope absorb a neutron and upset the neutron to proton ratio. And we're going to allow the electrostatic force, the repulsive force of the protons, to actually split apart the atom. Because when we bring in the extra neutron, we upset that delicate balance, right, of the overcoming nuclear force, overcoming the repulsive force of the protons. And when we do it, it's just going to fly apart all by itself. So now we have to look at what the probability of a neutron actually getting absorbed is. And that's where we talk about this thing called microscopic cross-section for absorption. Microscopic cross-section. All right, let me let this camera fade. There we go. Microscopic cross-section. So microscopic cross-section really is a probability, but we're going to think about it in terms of a target area. Because here's why it's important. I'm going to draw a graph here. And we're just going to call this big fancy phrase here, microscopic cross-section. We're just going to call it target area. Something that we can relate to. So the bigger the target area, the easier it is to hit. All right, so I'm going to put target area over here on this axis. And then what I'm going to do is I'm going to make this the neutron energy level. So this is neutron energy. And I'm going to put it in electron volts, where an electron volt is the energy of one electron passing through an electrical difference of 1 volt. So we know we're talking a tiny bit of energy. That's why we still have to deal with mega electron volts many times. Here's 0 mega electron volts. And like I said, here's 0 mega electron volts. And way out here, I'm going to put 3 million electron volts. And when I get a neutron from fission, when it is born from fission, and we haven't talked about that yet, but they're all going to be born out here in this very high energy spectrum. As a matter of fact, we'll define these spectrums. There's 3 of them right here. We're going to call this the fast spectrum. And we'll actually define fast right out of the gate. 0.1 MeV or higher is a fast neutron. And here's 1 electron volt. We're going to call this, if you're less than 1 electron volt, we're going to call this the slow spectrum. And then if you're in between these two, we're going to call it intermediate. And we're going to give this several different names, actually. Intermediate. Well, all of our neutrons that we're going to see are born way out here. Here is a prompt neutron, which we haven't discussed yet. Here is let me rewrite those. I'm going to do it in circles. Here's a prompt neutron. Here is a delayed neutron. Look at the target area while they're in the fast energy spectrum. There's a prompt, there's a delayed. So this target area, once again, is the probability. It represents a target area that these neutrons right here, both this, what we call a delayed neutron and a prompt neutron, and they're both just neutrons that were just born from fission. We'll worry about what delayed and prompt means in a sec, but they're both born at fast energy spectrums. If I want to increase the target area such that these very high energy neutrons, if I want to increase the target area of something, I need to slow them down. I need to go in this direction. This is going to be so important. I need to get from this fast spectrum to the slow spectrum so that I can increase the target area. So that another interaction can occur. Because if I said the target area is the probability or microscopic cross-section, which means the probability of an interaction occurring with a neutron, you can see while it's in the fast energy spectrum, the probabilities are kind of low. So somehow I'm going to have to remove the energy of the neutrons from the fast energy spectrum, 0.1 MeV or higher, to the slow energy spectrum. And that's what this is all about on this page. Now, it creates a new unit for us. Since microscopic cross-section in reality is just a probability of an interaction occurring, something that's kind of hard is when you start talking, if we were to throw, it's already hard enough, let's start throwing statistical probabilities in it. Let's make it easier. Let's essentially make the probability a target area and give the target area a unit. And what we're going to call that unit is barns, a barn. And you can think of it just like you're imagining. Here is a big barn. And if you got a bigger barn, you've got a bigger target area. A barn is in reality a unit that is equal to 1 times 10 to the minus 24th centimeters squared. So if you have a lot of barns, you have a large area. Centimeters squared is an area. It's not true. Well, it's really a probability, but we're going to use this to essentially depict probability via area. So if I told you 92 uranium-235 has a microscopic cross-section of 685 barns. You would be like, great, I don't know what that means but I can multiply it times that, and it would be 685 times 10 to the minus 24th square centimeters. Knowing that means nothing until you try and you compare it to another isotope. What if I told you that 5 boron 10, it has approximately 3,800 barns. So you can see that if I have boron target area versus uranium target area, boron represents 5 to 6 times the target area. Each atom of boron is essentially 5 to 6 times bigger in terms of what it looks like to the nucleus. It's not physically bigger. It's in actuality, it's just the probability that if a neutron was coming in here and had to decide which one it wanted to interact with, do I want to interact with this uranium or do I want to interact with this boron? Well, it is a no-brainer. It is 5 to 6 times more likely to interact with the boron because of the increased target area. But in reality, it's probability, because you already know the uranium is much larger physically than the boron, but there's a higher probability that the neutron will interact with the boron. That's because it has a higher microscopic cross-sectional area, 5 to 6 times. All right, we're going to look at this in detail. Now, there's different types of interactions that can occur. So when the neutron comes in, right, there's different types of interactions. Now, the symbol for microscopic cross-section is going to be this little tiny symbol here, right? That's this symbol. And there's a total probability or a total microscopic cross-sectional area for an atom. So there's a total probability for, say, 92 uranium-235. But there are different interactions. So we have to further break down this total. The two broad categories are, there's a probability, a microscopic cross-sectional area probability for the neutron to be absorbed, and then there's a microscopic cross-sectional area or ability for it to be scattered. Then we can further break those down. And we'll look at what the absorption reactions are, and we'll look at the scattering reactions. But there are two absorption reactions we were to break this down, if a neutron gets absorbed, there's the probability that it causes fission. Or there's the probability that it is just captured and doesn't cause fission. Each of these, the sum of these two, would be the absorption probability. There's a probability if it's absorbed, it fissions. There's a probability if it's absorbed, it gets captured. The sum of absorption and scattering are total. There's also two types of scattering reactions. We'll find out and define these. There is scattering probability that it scatters in an elastic fashion, and there's a probability that it scatters in an inelastic fashion. So the total probability of a neutron right here interacting with uranium-235 is called its total microscopic cross-section. Well, then there's also an absorption microscopic cross-section. There's a scattering microscopic cross-section. I could break this down further. There is a fission microscopic cross-section, a capture microscopic cross-section. There's an inelastic and elastic cross-sections. They're all separate. The sum of these essentially equals these, which equal this. So any type of probability occurring, absorption occurring, fission or capture are absorption reactions. And scattering can be inelastic or elastic. So we need to look at that in further detail. That's going to be super, super important.